All right, I am going to talk about the first part of current. There are two types of current in semiconductor devices, and I'm going to talk about the first kind today and the rest of it Thursday, and I'm also going to talk about excess carriers on Thursday, which doesn't take very long. The next homework is up, and you can do about half of it now, and by the end of the week, you'll be able to do all of it. I will have covered everything, so you should be set. And the next test is Tuesday next week, and it follows exactly the same format as the previous test, except, of course, the problems are different and cover different stuff, too. So, when we talk about current, No, I don't review but one time I sit and talk about stuff, but we do so many problems in class, and that's just not necessary. So once you guys get the hang of how it works, it's okay.
You said
Test 2 is next Tuesday. Yes, February 25th at 6:30 in this room. It goes fast. But we are like halfway through the semester almost, so that kind of makes sense. If you have 4 tests, then the second one will be about now. So when you have charged particles in a semiconductor, they're going to move at some point, because that's the whole point of having a semiconductor. Is you have charged particles and they're going to move, and in their moving, they're going to create current. But it's not as simple as with a conductor where you just apply voltage and they just go. There's actually 2 different mechanisms that work to provide current. One of them is drift current, and that's current that basically you apply an electric field and you have current. So that's one type of current. That's the most obvious kind of current you get, because you apply a voltage, you get moving charges, so that would make sense, and that's what I'm going to talk about today. The other kind of current is diffusion current, and diffusion is just when you have a high concentration of something and it moves to kind of spread out into a lower concentration to kind of even out the concentrations, and that happens also, and it's a completely different current mechanism, but that also does happen. So the net flow of current in a semiconductor is just due to these 2 mechanisms working in different ways depending on what's going on in the material. So when you have 2 types of semiconductors that are brought together, and right at the junction you have a lot of electrons and a lot of holes, you can get diffusion in that respect, because you have an area which has more electrons and less, and more holes and less, and so you do get some kind of movement there. But today, what we're going to talk about is drift current. Drift current is what is caused by an electric field. So we apply an electric field to a semiconductor, and it provides a force that causes charges to move. The electrons and holes move, and they actually accelerate. So drift is the net movement of charge due to this electric field, and then drift current is the net drift of the charge, which is good. And drift is affected by several things. It's affected by the density of charge carriers, how many charge carriers you have per cubic centimeter, which you now know how to find, so that's good. The velocity of charge carriers, which isn't really easy to measure, but their mobility is easy to measure, so that's something we actually can measure, and how strong the electric field is. So all 3 of those things kind of work together to produce current. We usually talk about current density rather than actual current, because we're talking about blocks of semiconductor material, and so generally when we're talking about semiconductor material, we often talk about current density, which is just amps per square centimeter. But if we know the area, then we can figure out what the actual current is. But a lot of times we just need to know the current per area, and then we can extrapolate from there. So mathematically, current is defined, or current density is defined by the charge density, which, like I said, we can find, and the velocity, which we can't find. So charge density, you already know how to do that. You can find the number of electrons or holes per cubic centimeter, and you're experts at that now, sort of. You still need some practice, but you know that it can be done, and it's not that difficult to do. And then you just multiply by the charge of the particle, which is always going to be 1.6 times 10 to the minus 19, so that's not going to be difficult. But the velocity is going to be a problem because we can't measure that. We can't go down in there and measure the speed of them because we can't even find them. So we definitely can't measure electrons if we can't really pinpoint where they are. So there are two things we can measure. We can measure the strength of the electric field because a human being applies it, so we know what the value of it is because we decide what the value of it is. And we do know the mobility of the charge carriers, the electrons and the holes. And that's something that's been studied by somebody who has a PhD and sat in some office and in a lab and tested it and found out what the numbers were and put them in a table just for you. So this is something we can look up. And therefore, we can say the velocity is just equal to the mobility times the electric field, which is easy to find now. We don't have to measure the velocity. We just need to know the strength of the electric field and look up the mobility. Therefore, when we look at holes, the drift current density of holes, or due to holes, is in the same direction as the applied electric field. So, in other words, if you apply an electric field, the way you would expect current to flow, which is conventionally from plus to minus, is the way that holes flow, because conventional current is opposite to electrons, so holes flow opposite to electrons, so they flow the same direction as the electric field. We find the charge density by multiplying the holes per cubic centimeter by the electronic charge. And then we can find the velocity by multiplying the mobility of the holes by the strength of the electric field. So the entire current density is just found for holes by taking E times the number of holes, and that little p is just the number of holes. I know you usually see a p sub 0 or whatever, but that's all it is. That's just how many holes you have. Times the mobility, which you can look up, times the electric field, which we decide what that is. So it's only an exercise in knowing what to basically look up and what kind of material you have. The mobility is going to depend on the material. So the mobility of holes is going to be different in gallium arsenide than in silicon than in germanium. But other than that, it's easy to look up. Electrons, pretty much exactly the same story, except they go in the other direction. That's the only difference, is they actually move towards the positive part of the electric field, so they move opposite. Everything else is exactly the same. We find the charge density by finding the number of electrons and multiplying by the charge. We find the velocity by finding the mobility of the electrons times the strength of the electric field. And we have drift current that is due to electrons. Therefore, the total drift current density is just the combination of the two. And that's it. We just add them together. So the charge of the electron and the strength of the electric field are part of both, so they're just there once. And then we just take the mobility of the electron times how many we have, plus the mobility of the holes times how many we have. Usually, pretty much, unless you have almost equal numbers of holes and electrons, which would really only happen in intrinsic material, one of them is going to be a couple orders of magnitude greater than the other. So in p-type material, you're going to have more holes than electrons, and you're probably going to have a couple orders of magnitude more. And then when you're adding you're adding on something that's so small that it really doesn't matter. So the majority carriers generally affect the current more than the minority carriers. The minority carriers are there, but they don't affect the current density as much. So usually when we find drift current density, we just approximate it and take the majority carrier and multiply that by its mobility and multiply by the electronic charge times the electric field. If you are scared to do that, just use the whole equation and you'll be fine. It's just that the minority carrier won't make a whole lot of difference in your calculations. So you can do it either way. If you're worried about making a mistake in estimating, then go ahead and just do the whole thing. So the number of charge of the mobility depends on temperature and material. So like so many other things, we can get the value of mobility for electrons and holes at 300 K, and we have to assume that we have reasonable doping concentrations, not just over the top. That's just one of those things, because if there's too many charge carriers, they're running into them so much, running into each other so much, they end up not moving around so well. Electrons generally move better than holes because electrons are moving freely in the conduction band. Holes are limited by the movement of electrons from hole and bond to bond to bond, and that's a completely different motion, so it's a different mobility. So let's say we have gallium arsenide, and we've got it says acceptor concentration of 0, which means there are no acceptors added, a donor concentration of 10 to the 16, and we have some assumptions. Remember, we talked about ionization, and I said we would always assume that it was completely ionized, which means all the donors that have been added have donated electrons. And we also are going to assume the mobilities that are given in the table. We're going to calculate the drift current density. And yeah, this is gallium arsenide. This is good. So, first of all, is this N or P-type material? N-type. There are more donors than acceptors. So you can tell right off the bat that it's going to be N-type because there are no acceptors. There's only donors, and donors are what give electrons. So it is N-type material. Therefore, the number of electrons is going to be approximately equal because the doping concentration is so great. It's much, much bigger than the intrinsic value of electrons, so we can say that's approximately equal to the number of donors minus the number of acceptors, and the number of acceptors is 0, so that's just going to be 10 to the 16 per cubic centimeter. And then we can figure out the number of holes by taking Ni squared over N. And we take 1.8 times 10 to the 6 and square it and divide by 1 times 10 to the 16. And we get 3.24 times 10 to the minus 4 per cubic centimeter, which is really, 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 really tiny. That's like a fraction of a hole per cubic centimeter. Don't make the mistake of assuming, well, this is a very small number, we'll make it 0. It's not 0. There are holes. And when you have a big sample, you will have holes in it. So keep the number even though it's only got a fraction of a hole per cubic centimeter. It's really a more proper answer. Let's see, what was I actually, oh yeah, I was supposed to find the drift current density. See, I forgot what I was doing here. There we go. All right, that's better. So we can get the drift current density. You'll notice the number of electrons is insanely bigger than the number of holes. So it doesn't matter if I put the number of holes in this calculation or not. It will not make a bit of a difference. There's like, 20 orders of magnitude between the two? So really, I can just take the values that are related to the electrons. So I can take the electronic charge times the mobility of the electrons times the number of electrons times the magnitude of the electric field. So I get 1.6 times 10 to the minus 19 times the mobility, and for gallium arsenide, we find it right there. So we take 8,500 for that value, and then we take 10 to the 16 for the number of electrons, and 10 for the value of electric field strength. And we get 136 amps per square centimeter, which seems like a lot. It's not doing anything really. So there's an applied electric field and there's a current, but that is a current density. That's not an actual current. So the actual current would be different if you multiplied by an actual area. It would come out being a lot smaller. So it's just a concentrated value. So these are not terribly, terribly difficult type of problems. So now I can't even see what I'm looking at. Okay. Ooh, there we go. All right. So mobility, yes. You have a question.
So what type of units did you say those were?
What type of?
Units.
Units. Amps per square centimeter. Or is it for mobility that you said units, or just for the current density?
Just for like the.
Yes. Yeah.
Oh, that subscript DRF is being driven.
Yeah. Yes. Yes. DRF is for drift, and DIF will be for diffusion when we get to that point. Yeah, there's like got to be two different kinds. All right, so mobility is affected by temperature, material, and doping concentration. When the temperature or doping concentration gets larger, there's more carriers available, and more carriers mean more collisions. Collisions actually kind of slow things down. It reduces the mobility because it can't move as much. It's just like when you're in a crowded room with a whole bunch of people, you can't move as much as you can in a room with not so many people. So the mobility depends on the time between collisions with something. So if you have a really, really long time between collisions, you have a really high mobility. If you have a very short time between collisions, you have a lower mobility. And this is divided by the effective mass of whatever the particle is. And always we multiply by the charge of an electron. So if we have a particle in a semiconductor material and we don't apply an electric field, it still moves. It still has drift. It just basically just moves around but doesn't really go anywhere. So it doesn't make any net movement in any particular direction. If we apply an electric field, then we still get that random motion, but it has a directionality to it. So the charges aren't just moving like this. They're all kind of doing this, but if you apply an electric field, they do this in a direction that actually makes sense. I'm getting close here. So, collisions are a problem. When particles collide, they collide all the time because they're always moving. And particles scatter and when change momentum, and it reduces mobility. I always like it when I am saying what I already said, and I'm saying it again because it's in the slide. There are two things that scatter particles when they run into stuff. One is lattice scattering, and that's when you have atoms vibrating because the temperature gets higher, and you can actually, because it's vibrating, you actually have things running into the lattice structure and scattering all over the place. The other is impurity scattering, where you add impurity atoms and there's other atoms and they run into each other also. So both of these influence how well electrons move. if we look, and a lot of this is theoretical, so I go through it kind of fast because there's the really calculating the drift current is sort of the calculation we make, and everything else is kind of just telling you why it is the way it is. The mobility related to lattice scattering is proportional to the temperature to the -3/2. We have temperature to the 3/2 a lot. This is inversely related to the temperature. So as the temperature goes up, on the left, it's just a simple graph of the mobility of electrons depending on concentration. So you'll notice on the left, as the temperature goes up, the mobility goes down, and as the concentration goes up, you're kind of moving this way because the highest concentration is on the bottom, the mobility also is reduced. So increasing temperature makes the mobility go down, increasing concentration makes the mobility go down. Also, for impurity scattering, we have again a relationship with the number of impurities and the temperature. This time it's related more positively to the temperature, but it's to the +3/2. And you'll notice that this is just telling you basically that as the impurity concentration increases down here, you get a tailing off of the mobility as you get more impurities. You'll also notice that pretty much the mobilities fall in different ranges depending on if you're looking at gallium arsenide or silicon or germanium. They're all kind of different depending on how they're constructed. The net mobility is the reciprocal of the reciprocal sum of the mobilities. So it's basically like taking resistors in parallel. You flip them over, you add them, and you flip them over again, and the net mobility is going to be less than either one of the mobilities that we're considering. So the lattice effects and the impurity effects are going to be combined to make a mobility that's less than either one of those. So both of them combine and create a mobility is less than either one of the ones we have. Now, we don't ever look at those separate things. We just look at the chart and we see the value and we just use it. So understanding why mobility is the way it is one thing, but you're only going to have to look it up on a table to see what the value is. So I am almost done. I have to talk about one other thing, and that's conductivity and resistivity and how it works. Conductivity is basically just a function. That's basically how well you're going to actually have charges move. And you'll notice it almost looks the same as the drift current equation. It's very, very, very similar. The only thing that's not on there is the electric field. If we take the charge of an electron and we add up the mobilities due to the electrons and the mobility and the number of holes, we can get the conductivity, and the resistivity is just the reciprocal of that. So the resistivity is how much current is impeded. Conductivity is how much current is allowed through, which is why they are reciprocals of each other. If we look at impurity concentration and I think this is silicon. I'm not even, no, yeah, it must be silicon because it says it's silicon up in the upper right corner. I did finally find that. But you can see with different type of dopants, with P-type it's doped with boron, and with N-type it's doped with phosphorus. And as the impurities go up, the resistivity goes down. So as you get more impurities, you get actually greater conduction, which makes sense because that's what you would want. If most of you, have you taken circuits, or are you taking circuits? I always ask this, and I never remember, but maybe it's in here. But the resistance of any material is just a function of the resistivity and the length and the cross-sectional area, no matter what kind of compound you have. And I can never remember where you guys learned this. Where?
Physics.
Physics 2, that's where you learn it. Somewhere in the world you do, because in circuits they don't mention this. But every single material out there has a resistivity. There are whole books that have tables of resistivities. This is why semiconductors are so cool, because their resistivity can vary, whereas most materials it can't. It's just set and doesn't change. So we can figure the resistance of any material if we know the resistivity and the length and the cross-sectional area, or the conductivity if we happen to have gotten that. And as you just saw, we can actually find that from parameters we've actually already found. So we're almost getting to where we need to go here. Current density is just current per unit area. Electric field is just volts per length. So both of these are really relating to current and voltage. They're just, because we're dealing with chunks of material, we put it in terms of per unit area. So voltage is just a length, a per unit length. Current is a per unit area. And then density is like a per volume. So we know these values. And now we can kind of relate it to just how do we figure out voltage and current and such for a chunk of silicon if we have it. So we can take the current density equation, which we had, and we can actually, since resistivity was 1 over E times the mobility times N plus mobility times P, we can actually put 1 over the resistivity there. So the resistivity is equal to the electric field divided by the current density. If you know the electric field strength and you know the current density, you can figure out the resistivity. And we can use that to figure out the voltage and current relationship. And all this is taking the volts divided by the length times the area divided by the current, and we basically derive Ohm's law out of that. We get the voltage is equal to rho L over A, which is the resistance, times the current, and we get V equals IR, which is kind of how it works in a bar of semiconductor material. So, second and final example, which you will need to know how to do. Let's say we have a bar of silicon and we know what the doping concentration of it is, and we want a current of a certain amount, 2 milliamps. We want a voltage of 5 volts. So already in the back of your mind, you can think, oh, Ohm's law. I know the voltage, I know the current, I can find the resistance. That should be an automatic thing for an electrical engineer no matter what. If you see voltage and current, you should think, oh, I can find the resistance. And that is actually what you have to do. So we want how big? We want the current density to be no larger than 100 amps per square centimeter, and we want to find the cross-sectional area, the length, and the doping concentration. So first off, we can find the area, because it wasn't explicitly given, but we can, because the area is going to be the current over the current density. So we have 2 milliamps over 100 amps per square centimeter, and we get 2 times 10 to the minus 5 square centimeters. So that is our cross-sectional area, which is good. We're going to need that. Now, as I said, we can find the resistance because we know the voltage over the current. So we have the voltage is 5 volts, current is 2 times 10 to the minus 3, and we'll get 2,500 ohms for that value of resistance. So we know that R equals rho L over A. So that means that rho L is going to be R times A. And we don't know L, that's one of the things we have to find. And we also don't know the resistivity, but we do know R times A. R was 2,500, and A was 2 times 10 to the minus 5, and that gives us basically 1 over 20. I don't use fractions very often, but it's a fraction. Now, this is the part that makes engineers nervous. So we don't know the length, and we don't know the doping concentration either. But there is actually a graph that we can use. It's kind of a trade-off graph. We can guess, and we can guess, and I'm going to go backwards for just a second here. There's a trade-off between what we guess and what we end up with. So let's say, let's say we would like, it has acceptor atoms, right? So it's p-type because it has acceptor atoms. And we can make an assumption. We're just going to say, and this is a big assumption. Oh, I can't even spell assumption. There we go. This is an assumption. This is just a guess. We'll decide on 10 to the 18 per cubic centimeter. And that means if that happens, if we go to this graph here, we assume, I wrote down 17 and I said 18. Oh well, never mind. I meant 17. Sorry. So let's assume 17 because, I think I came out the length was better with that. And if we look on here at 10 to the 17 and go over, we find a value of resistivity of about 0.2 ohm centimeters. Therefore, we can find the length by just taking 1 over 20 times the resistivity, which is 1 over 20 times 0.2. And I have no clue what that would be. That would be 25 centimeters? Is that what that is? Yeah, it's like 0.05. Yeah. It's what now? Tell me what it is. 1 over 20 times 0.2. Because what I'm looking at here isn't 1 over 20 times 0.2. I'm looking at a different number here. 1/4. That's 0.25. Is it 1/4?
Yes, it is. Yes.
Yeah, okay, so it's 0.25 centimeters. I went the wrong way. There are 3 things I can't do. I can't tell right from left. I can't remember the second thing I can't do, but the third thing I can't do is basic math. I'm terrible at it. I still count on my fingers. So anyway, the problem with this problem basically has to do with the fact that you have to make assumptions and we don't know. If we came out with a length that was completely disproportionate to the cross-sectional area, we could go back. This is kind of long for the cross-sectional area that was provided, so, but this is not the kind of thing I would make you do on a test because you get so nervous having to make an assumption, and So one other thing I'm going to mention, and this is just a mention thing, and then you can work on your participation problem because there's only 3 problems, so they're kind of short, is velocity saturation. Basically, what this means is that the carrier drift, when you have a low electric field, is going to be proportional and a linear function of the electric field. But as you increase the electric field more and more and more, the velocity actually comes to a halt and doesn't actually increase. And what happens even, you'll notice with germanium and silicon, they kind of go up and flatten, and this flattens. You'll notice with gallium arsenide actually has reduced drift velocity as it gets higher. And that has to do with the difference, radical difference in effective masses between electrons and holes in that. I would never ask you to explain that to me, so just so you know, I'm just telling you that happens. They can only go so fast, and they can't go any faster.